Hello, this is the Laser Harp Without Mechanical Strings project for Senior Design 2 with Group 6 for the fall semester of 2025. The team for this is Daniel Balasquita, which is me, for the computer engineer, Alejandro Pastrana as the electrical engineer, Alexis Shones as the photonics engineer, and Lazailis Zunia as the electrical engineer. This is Group 6. For the motivation and background, traditional harps we found to be large and fragile and difficult to play. And in this project we want lasers to replace the strings to make it more accessible for those with limited mobility. A frameless design emphasizes portability and inclusivity. And this project will combine optics, embedded systems, electronics, and computer software design in one device. The intended use for this is to have a STEM outreach for classrooms and museums and maker fairs, music exploration with the contactless play and visual appeal, and different from existing laser harps by it being compact, battery power, portable, and not dependent on MID/computer synthesizers. The goals and objectives. We want this to be a frameless harp where lasers act as strings. Basically, your reflection will be its input with your hand. The basic goals will include 7 beams across a 30-inch span, LCD that shows the octave and volume, battery operation of 30 or less minutes, and a detection latency that is less than 0.25 seconds. We also want this to be able to be plugged into the wall. In addition, the advanced goals is to use a culminating beam expander lenses, sync lasers with stepper motor, and use pre-recorded audio on a DF Player Mini and micro SD. For the stretch goals, we want wireless communication with an ESP32, the ability to record and play back stuff, and multi-string notes, basically chord support. Next, for the goals and objectives. The overall objective is to have a frameless harp that will be constructed with using a laser diode and a stepper motor to produce 7 individual sounds and use the obstruction of the strings to be detected by a photodiode. The detection will be from a reflection of the user's hand. A voltage reading of a specified level will trigger a musical note, which is saved on the SD card. For basic objectives, as you can read, we use a stepper motor with a mirror to create the 7 strings and photodetectors to detect its intensity. To optimize the angular speed of the laser beams, we will be using a stepper motor that is big enough to angle. Next, to optimize the dwell time by utilizing the dwell time, how long the beam will be at the position of the stepper motor by utilizing the stepper motor at the correct frequency and by calculating how many times per second the stepper motor will cycle. The device will also have an LCD to show the volume and octave of the notes. For the advanced goals, we want to design a lens system to culminate the diverging beam from a laser diode, then expand a beam to create a bigger beam for easier play. We also want to design a laser harp so that the stepper motor and the lasers are in sync. In addition, the device will have a separate memory storage element to store all the pre-recorded musical notes for a real harp or piano sound. For the stretch goals, we want to integrate wireless communication and external Wi-Fi module on board. And we also want to have the ability to implement chord support. These are the engineering requirements. For response time, we want something less than 0.25 seconds so it wouldn't be too noticeable for the user. 7 strings to represent an octave. We want the memory to be less than 80 gigabytes. The cost will be around $100 to $500, and the spacing between it we want is 0.5 inches to allow for a proper span. For further engineering requirements, we want the detection accuracy to be around 90 to 99%, the power consumption to be less than 200 watts, and the clock speed processing to be around at least 10 megahertz. The weight should be portable, so 5 to 25 pounds, and the size should be 1 to 2 feet.
Engineering specifications. The laser diode wavelength needs to be green. So we have 520 nanometers, and the power is 110. The collimating lens, focal length 7.5 millimeters. And then we need to expand the beam. So we have beam expanders. So the negative lens focal length is negative 24 millimeters, and the positive lens focal length is 48 millimeters. That will give us 2 times beam expansion. The mirror wavelength range needs to be between 380 and 750 nanometers just to cover the visual spectrum, and then we needed to collect the light, so the collection lens focal length is 25.4 millimeters. The photodiode spectral response needs to be able to see green, so 500 to 570 nanometers, and the active area is 13 millimeters squared.
Here, we're going to go over the general hardware design of the laser harp, how it's going to work, what components are going to be in it, how the components are going to be working with each other. To start, the way the laser harp is going to work is by having an MCU control a laser diode and a stepper motor simultaneously. The stepper motor will be turning back and forward at a high frequency while the laser is going to be turned on and off 7 times. This is going to be done so quickly that it's going to produce the illusion of 7 strings coming off the device. If a user disturbs one of those strings, a photodiode will detect the reflection. It's going to produce a current that will be turned to a voltage via a transimpedance amplifier. The MCU is going to read that voltage, then it's going to play a noise through playing a pre-recorded note through an audio module through some speakers. Additionally, there's going to be an LCD display that's going to tell the volume and also the octave level. There's going to be some user interfaces, a volume dial, and some buttons, a turn off button and a reset button. And there are also going to be some foot pedals that's going to be used to control the octave. In the PSU, there's going to be a 3.3 voltage regulator and a 5 volt regulator. The user is going to have the option to power up the laser diode by either laser harp, by either a wall outlet or a 12 volt rechargeable battery. The laser diode and the stepper motor are going to be driven by a laser driver and a motor driver, a stepper motor driver, respectively. And additionally, there's going to be a USB to UART converter to program the MCU. The microcontroller is the primary decision-making component in our laser harp. It'll be responsible with controlling the stepper motor and the laser diode to produce the laser fan that we're looking for. It will also be responsible for controlling any user interfaces, so any buttons, any dials, the foot pedals will be used. So when looking for MCU, we wanted to have a good amount of GPIO pins, able to read and write in digital and analog, and able to have a very fast clock speed. So we thought that after looking at multiple options, we thought that ESP32 Room 32 it might be the best choice for us. It's widely used, there's a lot of resources online, and besides adding a USB to UART converters, will be the right choice for us for this project. That will include the MCU, the ESP32. You can see that there's a lot of pins that will be used to control any user interfaces, the foot switches, the buttons, and the volume dial. It also includes a port for LCD display, and on the top left is the USB to UART converter that will be used to program the ESP32 once it's already in the PCB board.
For the sound storage of the project, we plan to use a DF Player Mini manufactured by DF Robot. You can see in the bottom right. This device offers support for 32 mini micro SD card, which will be used to store all the audio files for our project. The DF Player Mini also has its own amplifier and DAC installed on the module. This device only needs 3.2 to 5 volts to operate, so it will have a flexibility that will be good for our project. For the audio, we may need to use an amplifier for the project to project the sound. The 2 amplifiers that we will be using is the one that is built in on the DF Player Mini, and the other will be the LM386 audio amplifier. These 2 amplifiers are the DF Player Mini is a Class D amplifier, and the LM386 is an AB amplifier. Both of these offer very minimal distortion, and the cost is effective. While the other 2 are good, for the Class D amplifier for the mini digital amplifier and the TDA mono being an AB amplifier, they do offer cost-effective options and of flexibility, but we find our two options that we have selected to be the best for our project. Next, for the speaker. We will need a speaker that is able to handle the output power from the amplifier and produce a clean and audible sound. The speaker we selected was the Dayton Audio RS104 because of its ideal range to play notes and the sensitivity of the speaker. This will allow us to play all the notes of the harp and make them audible. As we can see, it is a sizable speaker and it does cost a little bit, but this option will allow us to have the most functionality with our system and to produce notes that are at the lower frequencies. While the other two options are functional and one of them is more cost-effective, we find the option we selected to be the best because of its versatility and volume capabilities.
In this slide, we'll go over motors. For our project, we compared stepper motors and servo motors to decide which was the best fit. Stepper motors use open-loop control, which makes them simpler to use, while servos need a closed-loop feedback system that adds extra complexity. Steppers also provide high precision for discrete steps, which is important for aligning the rotating mirror with multiple laser beams. Even though servos can handle higher speeds and torque across a wide range, we don't really need that level of performance for our harp. Instead, the stepper's accuracy, lower cost, and availability made it the more practical choice. The stepper motor specifically gives us enough torque at low speeds while keeping the design affordable and easy to integrate. Overall, the best option for precision, repeatable positioning in our optical system was the stepper motor. Going into a deeper dive in stepper motors, we compared 3 different types of stepper motors: permanent magnet, variable reluctance, and hybrid. Permanent magnet motors are inexpensive and simple, but they lack precision with larger step angles. Variable reluctant motors are lightweight, but they provide low torque and only moderate accuracy. The hybrid stepper, such as the NEMA 17 that we selected and are using currently in our project, combines the best features of both designs. It has small step angles, about 0.9 to 1.8 degrees, which gives very high precision. It also provides good torque and stability at standstill, which means that once the motor moves the mirror into place, the beam holds steady without drifting. These qualities make it ideal for applications that demand repeatable accuracy, like our laser harp. For our design, we are using one hybrid stepper motor with a mirror mount to create the illusion of 7 separate strings. The stepper rotates the mirror in small controlled increments, and each increment redirects the single laser beam to a specific position where it lines up with one of the harp's 7 string locations. By cycling through these positions quickly, the system makes it appear as though there are 7 individual laser beams present at the same time. This approach allows us to use only one laser diode while still producing multiple strings, which reduces costs, power usage, and complexity. The precision of the stepper motor is what makes this possible, because if the mirror alignment is even slightly off, the beams wouldn't line up correctly. That's why the hybrid stepper is the best choice for our optical system. When selecting a motor driver for our NEMA 17 stepper motor, we tested and compared the TB6600 and the DRV8825. The TB6600 is a very capable driver, offering about 4.5 amps per phase and supporting a wide voltage range, but is designed more for heavy-duty applications like CNC machines, robotics, or large motors where high torque is needed. However, it comes with some drawbacks for our project. It's a much larger external module that requires extra wiring and setup, and it costs significantly more. For us, it was simply an overkill in terms of power, and it was too bulky to fit in our compact design. The DRV8825, in contrast, is compact and easy to integrate. It holds up to 2.2 amps per phase, which is perfect match for the NEMA 17 stepper motor driver that we selected. It also supports a wide voltage range, but its small board design makes it much easier to fit in our PCB layout. One of the biggest advantages is micro-sipping capability, which allows us to achieve very smooth and precise motor control. This is essential for a harp because the rotating mirror needs to position the laser beam very accurately across 7 string locations. Now, for our display, we looked at 3 options: LCD, OLED, and TFT. OLED and TFT have great visibility and higher resolution, but they also cost more and use more power. Since our project only needs to show basic information like volume, octave, and key, we don't really need those advanced features those two displays have. We chose the LCD because it's much lower in cost, very power efficient, and simple to integrate. It connects easily with either I2C or parallel interfaces, which makes it straightforward to use with our system. Even though LCDs don't have the best viewing angles or graphics, they're more than enough for our project's needs and helps to keep the design affordable and efficient.
In the laser diode, we will be using two main voltage regulators to power up the Harp. It will be one for 3.3 voltage, one for 5 voltage. When looking at potential regulators, we wanted to have high efficiency, so it wouldn't produce heat, because heat is a major consideration when it comes to picking components. We didn't want the entire laser Harp to overheat. We also wanted it to have high current, just in case, and we also wanted it to have, if it was a switching regulator, we wanted it to have low frequency, relatively low frequency, just in case we get any EMI, any interference. Higher frequency regulators usually are more susceptible and more sensitive to EMI. So we thought that the LM2576 would be the right choice for us. Beside that regulator, we will be using two smaller regulators in the project. One will be the LM1117 for the transimpedance amplifier that we will be discussing later, and then the LM2664, which will also be used for the TIA. So here are the schematics for two of the regulators, the LM2576 on the left and the LM2664 on the right. The one on the left we will build two of those, one for 5, one for 3.3, and the one on the right will be used to produce a negative voltage of negative 5 volts to power up the transimpedance amplifier that we will again discuss later.
Moving to the photodiode selection, we picked between 4 photodiodes. The main considerations is it needs to be able to see green. The active area needs to be relatively large, and then it needs to have a faster rise and fall time. And the cost. We picked the FDS 100 mainly because the active area is 13 millimeters squared, which is relatively large compared to the other ones. And then the cost is only $17.55. The second best contender is the FDS 1010 because the active area is 100 millimeters squared, but that was $65 per photodiode. The laser diode selection, again, picked between 4. The main consideration with this was the output intensity. We want something that has a higher intensity because we want to be able to see the beam. It's really important to see the beam because that's the strings, and if you can't see the beams, you can't see the strings. So we have a higher intensity laser, so we chose the 110 milliwatt. It is more expensive at $41 per diode, but we need the higher power.
Laser diodes are sensitive components. They tend to break, they tend to get damaged, they get a shorter lifespan if they exceed operating values. Laser diodes also increase in conductivity when they increase in temperature. So it is important that we regulate the temperature, we regulate the current, and we regulate the voltage of the laser diode when we drive it. So that's one reason why we're using a laser diode driver to effectively, safely use the laser diode without it breaking. So for this project, we're using a constant current driver based on the LM2596S. And to toggle it, we will be using a 2N transistor, and that will be connected to the MCU to toggle it effectively, so we can get that synchronized pattern with the stepper motor.
There's 3 things that we really wanted to accomplish. When choosing the laser diode, it has a broad emission, so you need to collimate that light. In order to do that, I've chosen an aspheric lens with a focal length of 7.5 millimeters. We also want to ensure that the beam size is large enough so for easy playability and for easy visibility. So to ensure that, I created a 2x magnification beam expander. So we have a negative lens with negative 24 millimeters and a positive lens with 48 millimeters, and that'll create the 2-time beam expansion. Then we need to collect the light after it's been reflected off of the hand into the photodiode. So in order to do that, I chose this collection lens, and it has a focal length of 25.4 millimeters. And the image below the table is my ZMAX simulation. As you can see, the collimating lens is at the left. It collimates the light, then goes into the negative lens, which expands the beam, and then the positive lens collimates the light again, creating that 2-time beam expansion. We have the laser diode, which goes into the collimating lens, then the negative lens, positive lens, which then goes on the mirror, which is attached to the stepper motor. The stepper motor is moving at a very fast frequency, which creates the beam fan. The beams are then projected upwards into a beam dump, and then the user will place their hand in the beam path, interrupting the beam path, and that reflection will reflect into the collection lens, which goes into the photodiode, then playing the sound.
A very important part of the project is the inclusion of a transimpedance amplifier. A transimpedance amplifier is a low input, low output impedance current to voltage converter that would be used for the photodiode. The idea is to connect the photodiode to the transimpedance amplifier. Any current that releases from the photodiode will be amplified by the TIA and measured by the MCU. Using a TIA ensures that the MCU isn't drawing current from the photodiode. When we started testing the amplifier, we were using a typical TL084 amplifier, operational amplifier, but we decided to use an OPA 380 because it is an amplifier that is specifically used for transimpedance amplifier, has a high frequency. It is good for us. Additionally, as you can see in the schematics below, we will be also using an LM1117 regulator to regulate a 5 voltage to a very stable 3.3 to bias the photodiode. By biasing the photodiode, we're able to get a higher responsivity, and we're making it more sensitive to light. Additionally, we will also be using an LM2664 to generate a negative voltage for the operating amplifier.
Next, for the software design. We want the system to be fast and responsive, so C++ will be used because of its simplicity and speed of the language. Arduino IDE will also be used for uploading the code. The software design is relatively basic. It will involve straightforward commands and processes such as reactions and hardware startups. Interrupts will be needed for all the synchronous action of all functionalities of a project. As you can see by the flowchart to the left, you can see that everything needs to be in a constant loop in order to function and allow for synchronous actions. We can see what inputs will be necessary for what reactions of it. And it will always, even if the user does nothing, it will always loop back to waiting for user input. And we want to have a boot up process for the system. And we will plan to add a boot down system for the LCD as well.
PCB design for every section of this project. We'll first go with the main board, which includes the MCU. The MCU, again, will be used to control the stepper motor and the laser diode and any user interfaces like buttons, pedals, and dials. As you can see, there's a lot of buttons, a lot of pins used for the user interfaces. LCD will also be included. In the top right is the USB to UART converter, which will also be included. And below are the pins that will be used to connect to the regulators and to connect it to the main power generator. The transimpedance amplifier on the left and the audio module on the right. The transimpedance include the LM1117 3.3 regulator and the OPA 380. There's pins on the middle, on the central PCB that will be used to connect the photodiode into the PCB. On the right is the audio module, contains the DF player and the LM386 amplifier. There's going to be pins on the right side that will be connected to a speaker that will be outputting noise. Two of the regulators that we're going to use, the LM2576 on the left, the LM2664 on the right. As previously stated, the LM2576 will be used to generate a 5 volt and a 3.3 voltage for the components. and the LM2664 will be used to create a negative voltage for the operating amplifier. The final PCB from our project is going to be the stepper motor, which will include the DRV8825 driver IC. It also includes a potentiometer to limit the current being drawn by the stepper motor. And there's on the right side, there's going to be the pins that will be connected to the MCU. Some of the pins will probably not be used. And this is probably going to be the first iteration of our PCB, so things are subject to change.
Next, I will go over prototyping and testing. We started by comparing two stepper motor drivers, the DRV8825 and the TB6600, to see which one handled the NEMA 17 stepper motor more effectively. The test showed the differences in smoothness, torque, and microstepping, which helped us decide on the best option for design. Next, we focused on the stepper motor itself. We verified that it could move in small, accurate steps, which is critical for creating a consistent laser beam fan. From there, we designed a transimpedance amplifier using a TL84 op-amp. The circuit takes a small current from the photodiode and converts it into a measurable voltage, which lets the harp detect when the beam is blocked by the player's hand. That's how the notes will be triggered. We also constructed a laser diode module with a heat sink and lenses and connected it to the MCU so it could be toggled at the correct frequency. Finally, we tested the user interface, including buttons, pedals, and dials, and confirmed that all the inputs worked as expected. Looking ahead, there are two main areas we're still working on. The audio system itself needs more testing to make sure the sounds play consistently, and we're continuing the synchronization of the stepper motor, mirror mount, and laser diodes. Getting all three to work together smoothly is essential for the harp to perform the way we designed it. Now, I will go over our budget. Our total estimated budget for the laser harp is about $860. The largest cost comes from the photonics components, the lasers, sensors, mirrors, and mounts, which make up around $500 since they are critical for the instrument's function. Electronics like the microcontroller, PCB, and audio output are about $140. Power, audio, and the frame materials are relatively smaller in cost, each around $50 to $60. We also included miscellaneous expenses for connectors and mounts. Overall, the budget stays under $1,000 while covering all necessary parts to build and test the harp effectively. Now, for our work distribution, each member of our team took on a specific role to make sure all parts of the laser harp came together. Daniel, our computer engineer, is in charge of the firmware and software development, making sure all the subsystems work together as one instrument. Alejandro, one of our electrical engineers, focused mainly on the power system. He designed the power supply, selected voltage regulators, and also worked on parts of the PCB layout. Alexis, our photonics engineer, handled the laser side of the project. She worked on selecting the laser diodes, aligning them with the mirror and stepper motor system to create the virtual strings, and also helped design the lens setup. And I, the electrical engineer, focused on hardware design and integration for the laser harp alongside Alejandro. My responsibilities include helping the software side of testing and integrating, selecting and organizing key electronic components, and verifying that all wiring and connections between components, circuits are properly designed for reliability and efficiency. This slide showcases our progress and future milestones. So far, we made strong progress in the early stages of our project. Research is almost fully complete, which gave us a solid understanding of the components and design choices. Design work is also close to 90% done, and most of the parts have already been selected. Right now, we're starting the construction phase where the components are being assembled and integrated. After that, we'll move into testing, where we'll focus on making sure the stepper motor, lasers, audio system, and user interface all work together smoothly. Overall, we're transitioning from planning into hand-on building and testing with the goal of having a fully working prototype in the next phase.